The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everybody. Thank you for joining us today. This is our first edition of Just Ask Paul. It is exactly what it says. You submit questions to Paul, Paul goes through them, and he answers them. Just a little bit of housekeeping so you know how this works. We have gone through the questions that you submitted. Paul has put together some slides that he'll go over in response to that. You have the option of adjusting how you view this presentation next to each of the photo icons. So underneath Paul on the right-hand side and underneath the presentation on the right-hand side, you can choose to enlarge them. That's going to adjust how you see this feed. Do so as you wish. I personally am watching it as a side-by-side, and you can still see and read the questions just fine and his responses. So with that, I'm going to turn it over to Paul, and we will get started.
Good morning, everybody. Just for 2 more minutes of background, my name is Paul Brankleon, Director of Research, Education, and Technology here at NADCA. And I've got about 35 years of casting experience, magnesium, aluminum, zinc. On the aluminum side, from small tonnage, 150 ton, all the way up to 4,400 ton die-cast machines. So with that, I'm going to go through the questions that were submitted. There were additional questions that came in after I already put this together. We're going to plan on additional editions of this starting next week to answer those questions and follow-on questions. So let's get started. So the first question is, what would be considered the industry standard for porosity in screw holes? And is there standards defined that all die casters would recognize? So first of all, porosity is a pretty broad topic for die casters and OEMs or customers. So the condition of the casting, the type of casting, whether it's a leak-free casting, a pressure-tight casting, a structural casting, porosity is a major concern. Porosity in threaded holes is a concern because when you're looking at the threaded hole, you're looking at the integrity of the product, and then we all have our customer expectations. So let's kind of expand on each one of those points really quick. Being in the industry for as long as I have, porosity have had standards that each customer has developed. There is not a universal standard for porosity that exists that all OEMs and all die casters adhere to. So I've worked with standards with General Motors, with Ford, with ZF, with TRW, and many other individual customers. And frankly, they're like a book. And as you read that book and understand what they want, they have external porosity on all machine surfaces. They have internal porosity. They have porosity in threaded holes. They have porosity in KPC or critical zones of the casting. They have leak-free porosity. And then some castings, like structural castings, have the mechanicals, the tensile yield and elongation, that if porosity is present, it affects the elongation. So it's just an imposed standard that if there's porosity present, we're going to affect the mechanicals. So let's just talk about threaded holes for just a few minutes. As we see porosity, once again, it's going to be in a die casting. The question is where's it coming from? Is it from our die, trap gases, in our design, in the process itself? Are we trapping gas in the process? So a lot of sources for porosity. When we look at tapped holes, the reason it's a concern in tapped holes is because of thread engagement and the thread integrity itself. So when we're looking at the thread engagement, we want to make sure that if we have porosity in those threaded areas, as we do a torque test or a pull test on the thread, that the porosity is not affecting the overall thread strength. And then one other comment here on the slide is, thread size or thread engagement. As we have, fine threads or coarse threads, finer threads are going to be stronger than coarse threads. So if you've got a coarse thread and porosity, you're going to potentially affect the integrity of the thread. We can calculate, we have a lot of formulas, we can calculate the actual thread percentage in die casting and casting aluminum and then threading those holes, we're going to thread those holes using either a form tap or a cut tap. And if we're forming those threads, we're actually moving the material and not removing material. A form thread is stronger than a cut thread. But the problem with a form thread is you have to follow the draft of the hole. So at the top of the hole, you're going to have less percentage of thread than you will at the bottom of the hole. So if we have less percentage of thread and we form those threads and we have porosity inside that hole, porosity was that was at the surface, shrink or gas, it's going to affect that thread integrity. So, going back to the original question, what is the standard? Well, once again, there isn't one, but I can tell you that external porosity on most standards is 1 millimeter. So 40 thousandths of an inch or less is allowed on machine surfaces. And then with most standards, they then specify a location. So how much porosity you can have. I can have 2 indications or 3 indications in a diameter, in some diametrical area or some area. So inside of a threaded hole, we were typically only allowed 1 to 2 indications of 40 thousandths or less. If more porosity was present on the threads, then those castings became scrap. So I know that didn't necessarily answer the question as far as is there a standard or what's allowed. I'm telling you have to deal with your customers and you have to work with what percentage of thread you want versus what the porosity is going to take away. So each customer is different and you're going to have to work with your own OEM on those. One other comment is when you're dealing with your threads is you can adjust the D or the H level and adjust the size. That doesn't necessarily affect the porosity, it's just a point of interest. There are publications that can help you on minimizing porosity. I just threw one up here for the publication 516 on a guide to correcting porosity. Moving on to the next question, is there a commonly used hourly rate to operate die-cast machines of various tonnages when preparing a quotation? So the short answer, unfortunately, is no. There's not a uniform cost associated with a specific tonnage of die-cast machine. I'll show you some additional data here in just a minute, data that dates back to, I think, 1994. The fact is that each machine size does have a cost and that cost increases with machine size. So a 20-ton is going to be lower cost than a 100-ton, lower cost than a 1,000-ton, lower cost than a 4,400-ton. So, the long answer is when we're looking at the cost of a process, cost of a die-cast process, so all this list and the next 2 lists all are just what go into costing our process. So we have the cost of raw material. So we're dealing with the guys that are making the aluminum, cost of the raw material, cost of the setup operations, accessory costs, how much raw material we're going to be using, the defect rate, so what's your scrap rate, and then within every area of the United States, energy costs are not uniform. So our gas costs, our electricity costs. So with gas, we have the cost of the gas and the cost of distribution of that gas. We have the raw material sublimation, which is going to be the scrap. So what is our dross loss? Are we at a 1% dross loss? Are we at a 5% dross loss? Are we melting in a reverb? Are we melting in a stack? Then we've got depreciation schedules and accounting systems that are going to come into this. Then you've got a cost of labor. Is it a large OEM, a die casting company that has minimum wage standards, or am I a very small die caster and I don't necessarily have minimum wage standards, but I don't have to compete with those guys. So the cost of labor is going to vary. Then we get in just to the cycle time. So we've got all this previous stuff and then accounting factors. Now we're into the cycle time, which is, we all think of, costing a die cast machine is amortizing the machine and then how long it takes to make a part. Well, frankly, there's a lot more that goes into it than that. So we've got the cycle time of the entire process. the cooling of the alloy, lubrication of the die, extraction from the die. So once we get past the process and the actual casting, making the part, how long did that take? Then we've got other items that affect how well we're going to make a part. So I put these in as penalties. So penalty for surface roughness, penalty for dimensional tolerances. So tighter tolerances are going to potentially lead to higher scrap, and that higher scrap is going to affect our overall costing. And lastly, we've got the setup time and scrap, and then our batch sizes. Are we running 100,000 parts? Are we running 10 parts? So amortizing a setup over the number of parts we run is also going to affect the cost. So jumping to this particular study, so this is a study from 1994, and I put tonnages. This study was done in metric units. I put tonnages to the far left, actual clamping force. And I've circled what this study came up with in 1994 for a 100-ton up to a 3,000-ton die-cast machine. So the operating rate in US dollars per hour ranged from $66 an hour up to $218 an hour. Now, mind you, that was 26 years ago. So 26 years ago, these were the costs. We've had labor costs, we've had energy costs, we've had, cost of doing business has moved dramatically from 1994 to 2020. So if we take into effect the cost of economics from then to now, we could kind of extrapolate what a 3,000-ton or a 1,600-ton machine, 1,600-ton at that time was rated at $132 per hour, and what would that be with that cost of living change? One last comment from that same study is these are all the visual representation. I know this is kind of an eye chart, but this is a visual representation of all the things that go into costing our final product. And we can see that here. So we have this item here, which becomes the total cost and the part cost. And then all of the inputs above there, processing cost, alloy cost, energy cost, tooling cost, setup cost, all of those items all leading down into a total product cost. So you just get a kind of visual representation of costing those parts. Moving on to our next question, and that is, shock towers are a growth opportunity for high pressure die casting. Seems that magnesium would work well also. When will we see high pressure die cast magnesium shock towers? Well, right now, I do know of a couple of magnesium die casters that are now making structural components. The structural components they're starting with are grill opening reinforcements. And so these are being cast with the same integrity and virtually the same type of process as aluminum structural castings. So up in the far right-hand corner, I've got a picture of a shock tower. I personally made that particular shock tower for several years, and structural casting, heat-treated product, no blisters allowed, high elongation alloys. So with those alloys, the magnesium group is now moving into that, and there are magnesium casters today that are making these parts. Can they make the shock tower? I don't know that. I think the design would have to be adequately modified for the structural requirements and the elongation requirements. But I do know that the magnesium alloys, especially like the rare earth element alloys, definitely have the ability to meet the properties and to meet the elongation. Can they meet the tensile and yield? I don't know that. But I do know that magnesium is a good opportunity, a good lightweighting opportunity, but it's going to have to meet the same structural, zero porosity requirements that the aluminum alloys are having to do to make these type of castings. Moving on to our next question, what is the best way to initiate process monitoring of die cavity surfaces with an infrared camera? In my opinion, the best way to initiate that is just by using handheld devices like a Fluke or a FLIR or some equivalent device. There's a lot of different devices on the market. I believe that infrared monitoring or dye temperature monitoring is essential to understanding what the temperature of the dye steel is, especially your ejection temperature. So knowing that process variable, we have the ability to look at what our distortion is going to be. We can see our cooling of our mold. Can we use conformal cooling, in specific hot areas? Do we need to change our dye spray for specific hot areas? So I think that these infrared monitoring devices are absolutely essential. And frankly, with the cost of a very rudimentary one, they have ones that will actually hook up to your phone, made by FLIR and Fluke. But using an infrared device is definitely essential to the process, and a handheld device is probably the best way to get into this. Now, with that said, I do know of several die-cast companies that are using infrared monitoring devices that are actually attached to the die-cast machine. So they've got these devices, they're monitoring the cover half and they're monitoring the ejector half of the mold, and they monitor every shot. And they can take up to 200 readings on the cover, 200 readings on the ejector, and then they can monitor that and have the ability to actually set up zones. So I can set up a temperature zone, and I want my ejection temperature to be 485 to 505. And if that zone gets outside of that, it can actually alert my monitoring system that I potentially have a defect or I have something I need to pay attention to. So those devices do exist. They are costly, more costly than a handheld unit, but they have some drawbacks. So the major drawback or difficulty with using those type of devices is keeping that camera lens clean. Now, I have seen some recent developments where they actually have a lens, an external lens, not a lens on the camera, but a glass screen or a plexiglass screen that actually covers the lens during the spray cycle, which is where we're going to get a lot of debris blowing around the mold and potentially up onto the camera. So it actually takes an image and then closes off the camera to allow the spray cycle and the extraction cycle to take place, and then trying to prevent that lens from getting dirty. I can tell you with those devices also, because I've used one of those, they still have the ability to get the lens dirty. So you have to set up a PM, so many shots, so many cycles. I've got to get in there and clean the camera lenses to make sure I'm getting good images from my infrared system. Once again, those systems exist, and I think they're more high-end and they're more process related, where you have to pay attention to more variables in your process than you have to today. So many handheld devices, many what I would consider economical devices, and I think an infrared device is essential to the die-cast process. If you don't have one, you need to get one. So we had a question, Paul, how tall are you? So at last measurement, I'm 5'11". That really doesn't help us make better, faster die castings. And I want to thank Dan for that question. All right, moving on. What is the mean difference between ADC12 and K alloy? So each alloy has very specific properties, and those are going to come down to the chemistry. So when we think of ADC12, that's very close to a 383 alloy. And typically ADC12 is compared to 380. So when we're comparing ADC12 to an A380 alloy, it has better fluidity. It has better resistance to hot cracking at elevated temperatures. So that alloy has a slightly higher silicon level, a little bit controlled copper level, but when comparing directly to 380 alloy, it can improve the fluidity and make a more fluid tight casting or a leak-free casting. K alloy, on the other hand, is a highly corrosion resistant aluminum alloy that has slightly higher properties than the ADC 12. So when we're looking at the mechanical properties, so this chart, and in this chart I got ADC 12 here and K alloy here, and with that I've got the elongation, tensile, yield, impact strength, shear strength, hardness, and we can see that the elongation, these are cast tensile bars, so we need to be aware of how we're making those specimens that we're going to then be testing the mechanicals on. These particular data points come from cast tensile bars, so we can see that K alloy over ADC 12, as a direct comparison, has better elongation, slightly less tensile, slightly less, or excuse me, a little bit higher yield strength, and a little bit higher hardness. So mechanicals, I would say the biggest difference here is going to be the elongation of the alloy. Here we're now looking at the chemistry. So the chemistry, direct comparison of K alloy on the left and the aluminum 383 or ADC 12 on the right. And we can see that the copper is probably the single biggest difference. So the K alloy has extremely low copper, and I've made this a little bit larger, so we can see the copper levels of ADC 12. There are several different specs. So customers have specs on ADC 12, and some customers tighten this range, but overall, it's going to fall somewhere within 1.5 to 3.5% copper. Another change is going to be the manganese. So the manganese in the K alloy is a controlled level of 0.5 to 0.6, and the manganese level is a max of 0.5% in ADC 12. So I can have from 0 to 0.5% manganese in ADC 12. This is a requirement, if I'm going to drop this copper level, control the iron level, and pretty much maintain the silicon level, 9.6 to 12 in ADC 12 and 9 to 11.5 in K alloy. So once again, our biggest difference, single difference, is going to be the copper levels. So with that reduced copper level, we're going to get much better corrosion resistance as compared to 380, 383, ADC 12, because those copper levels around that 2.5 to 3.5% copper levels are going to give us much higher galvanic situations, dissimilar metal situations where we're going to get corrosion. So any kind of introduction of salt onto the casting surface on an ADC 12 casting is going to lead to corrosion. Now there are other choices out there as comparisons to K alloy, and that's going to be using like an Oral 5 alloy or a 518 alloy. Now 518 is an aluminum magnesium alloy, and so magnesium is the next highest constituent material. Virtually no corrosion. It's used in high electrical and high corrosion environments for 518, but I'm going to tell you it's much more difficult to cast than Oral 5 or K alloy. The aluminum silicon alloys with good fluidity are much easier to cast than a 518 alloy, but those are just choices. So there's kind of a direct comparison of the differences between K alloy and 383. Summing that up, mechanicals, virtually the same, a little bit higher elongation for K alloy. The chemistry, definitely the copper change as a low level of 0.5 to 0.08 on the K alloy does lead to better corrosion resistance. Moving on to the next question. What are the top 5 tips to improve and sustain a SMED program? So as we start to understand what SMED means, SMED is single minute exchange of dies. And what I've stuck up here is just a broad view, broad brush of a die setup. So when we're exchanging dies, we're pulling a die, we're setting a new die, we've got to assemble the tool, we've got to move the tool, then we've got to preheat the die, shut down the die that was in there, remove the previous die, put in the new die, get it ready to shoot, test it. If we pulled the previous tool, we're cleaning it, and we're transferring the previous tool back to storage. So that's a broad view of setup. Bottom line is we're exchanging tools in the process. What this chart is meant to say is what are external events and what are internal events. So if we're looking at SMED, we want to know everything that has to be done internal to the process and what things can be done when we're not running the die-cast die. So the real question was, what are my top 5 tips? So my number 1 tip is you've got to do measurement. If you don't measure something on a continuous basis, you have no idea where you really are at. So timing is everything. You've got to measure it. And one way is just putting a clock on a stand, getting a large clock, not a wristwatch. Hey, we started that at 2:45 and we ended at whenever. Now you want a clock, a timer clock where you can set it up. When I make my last good shot, I push start and it now starts timing. And it times that setup to the next good shot. So if you're doing a SMED event and you are following the single minute of exchange of dies process, you're taking all those external events, you're trying to make things mostly external and minimize your internal events. So your tooling's got to be ready, all of the tooling. So your trim die, your die-cast die, your knockout bars, your cooling systems, your cold chamber, shot sleeve. Every component needs to be ready when we shut that previous tool down. We think of that and then we don't have something ready. The cold chamber wasn't holding out. I don't have a tip ready. I don't have this. So all of a sudden I've now got to stop and wait for a tip. I'm waiting on the tool room. I'm waiting on maintenance to come over and check a core switch because I'm not getting a core switch. All of these things are going to slow down our setups. So everything's got to be ready. We've got to think about that readiness. My point 3 or item 3 is tool organization. Having done this many, many times in my career, a tool cart is a great concept. And I'm going to tell you, it's the best way to go by having all the tools organized so we know where everything is, we have everything ready to go. And then having an organized tool cart. I've kind of thrown up 2 pictures here of a organized tool cart and a disorganized tool cart. Hey, I'm hunting for that socket and I've got to go through my whole toolbox to try to find it. Well, frankly, that's an individual toolbox and it's a mess. We've got to have an organized tool cart. I'm also going to state that easier said than done. A tool cart is something that's got to be maintained. If there's things that come up missing on that tool cart because somebody needed a wrench or somebody needed a bolt, they've got to be replaced. And I'm going to tell you, it is something that's got to be maintained, and it's difficult to maintain it. It is not a simple task. It's not a Nike project. Just go do it. Just make it happen. Frankly, it's something that's got to be maintained and maintained over and over and over. Point 4 is practice. We think of NASCAR, and frankly, I watched Ford versus Ferrari several weeks ago. Great movie. And I watched the NASCAR team in that movie move at what I would consider a snail's pace. And you look at NASCAR today, and they've changed all 4 tires and fueled the vehicle in 8 seconds or 5 seconds, some unrealistic number, some number that is the standard for today. So practice the die setup. Understand, hey, we're going to do it in this fashion, and this is the order of setting the tool. And then lastly, make sure you have a setup team and there's a leader. Just because we have 2 or 3 guys on a setup team, one of them needs to be in charge, and the other 2 are the squad or the team. You can't have 3 leaders and everybody moving in different directions. So if one guy starts to run into a problem, the leader's got to make a decision. Hey, let's all move to that task because we're having a little more difficulty there. Or, you know what, that task got done early, so let's move to these tasks. So within that setup team, 5S, cleaning is a part of our daily lives. Cleaning is not part of setup. We don't go in there and start, cleaning around the whole die cast cell when we're doing a die setup. We can have a cleanup team do that while we're doing the die set. But if we're going to minimize die setup time, we have got to focus on 5S as a daily event so that we're not tripping over gates and castings as we're trying to do a die setup. Handling, moving the tool to and from the die cast machine, the die should be sitting there. It should be preheated, and it should be 10 feet away from its setup location. It shouldn't be half a plant away in the tool room, and then we hook it up on a hoist or we put it on a lift truck and we move it to the machine. That moving time is all external events, and they need to be maintained as external, not when we shut the machine down and we go to the tool room and get the die. And lastly, the cooling systems. I think of any die setup process, setting up the water lines or the cooling lines or the oil lines is probably the single length, the single piece of time that takes the longest. So I've put on the bottom here several different companies and several different methods to hook up water lines. So if we look at this unit right here in the middle, this one, if this was all cooling water, processed water, we could have cooling lines here, and this piece stays with the die. We could have cooling lines hooked up here, and this thing stays with the machine. So we have a standardized cooling system. We bring this in, we attach it, we clamp it shut, and we've now just hooked up 12 water lines in one fell swoop. And these can be manufactured, frankly, in-house, or you can buy these devices. But bottom line is, there are ways to minimize your cooling and your cooling setup and to make this much more efficient. In the same vein, this next question is, what is considered world-class for setting up a tool for changeover time for 1,600 ton, 2,500 ton, and the 3,500 ton die cast machine, considering the water lines, chambers, and the manifolds are going to be constant? So world-class, I really can't answer that. I can tell you what I know as best in class by seeing a lot of different die casters and knowing their setup times. So what I have seen is a 1,600 ton multi-slide die be set from last good part to first good part in 4 hours. Now, that wasn't a phenomenal feat for this particular company. This was a standard event. They really practiced SMED and focused on getting the tool in, getting it set, getting the previous tool out, and making that next good shot. And they were monitoring the time. So for a 2,500 ton machine, I've seen die sets in good die sets, 7 to 8 hours. And for a 4,400 ton machine, done in about 15 hours. Now, the other side of that is I've been in several plastic molders, plastic injection molders. Now, their die cast tools, or their tooling, not die cast, they're injection molding tools, very similar to die cast tools. So a 2,500 die set, I've seen that done in 21 minutes, start to finish. Now, the manifolds and all the cooling were all actually attached to the tooling. So as they clamp that die using die stakes onto their plastic injection molding machine, all of their cooling lines attached at one time to manifolds. So nobody was actually attaching anything to the tooling. I haven't seen that done in but 1 or 2 die casters, and only on a limited basis. So what can be done and what is being done, very different. So this is just examples of what I have seen. So I've gone through the majority of the questions. Now, I had a few other questions, one on some classes, one on additive manufacturing, and I'm going to save some of those and use those for our next edition. So if you have questions that you want or you want to have a discussion on what you've presented to me, there's my email, there's my phone number. You're welcome to give me a call. And we are going to be planning on doing the same event because we've got additional questions that have come in sometime next week, and we'll set up that time shortly. So if you have any questions, you can actually raise your hand or type in the question, and I will be able to see it.
So as Paul said, we are going to kind of open it up. This is more for clarification. Any additional questions that are, completely unrelated to what we discussed today, those we will take care of during the next episode of Just Ask Paul. But I think Paul's going to pop up those questions and see if any of that is just kind of a follow-up to any questions that were asked. Again, email us. You guys should all also have the link to that question submitting page. If you don't, just email me directly. You can email webinars@diecasting.org, catlit@diecasting.org, or you can email Paul and we'll get you that link to submit additional questions as well. So Paul, do you see where some of
I do. I have the questions open. So the first question says, should 4 cameras be used to obtain each angle of both halves? Well, I can tell you 4 cameras is better than 2, but it really depends on the size of your tool. If you've got an extremely large tool and you want to have more clarity on specific zones of the cavity, it would be better to have either cameras put in specific zones or to have multiple cameras. Cameras I worked with that were actually mounted to the die-cast machine did a fairly good job of measuring all the heat on the cover half and the ejector half, and they were about 8 to 10 feet away from the cavity. So they tried to stay out of the mist area. The camera lens still got dirty and they still had to be cleaned. It was still a problem. So more cameras are better, or putting those cameras on specific zones. The next question is, what is your recommendation for parameter temperature when we are working with A150, which is 99.7, I think, percent aluminum? So you've got an alloy that is nearly pure aluminum. And when you're dealing with pure alloys, the solidification range is extremely fast. So the alloy temperature is going to be specific to that alloy. I can look that alloy up and I can tell you from the properties of the alloy what it's going to be, Jamie. So if you want to follow up with me with an email, I can get back with you what would be the book recommended casting temperature. So if you're actually ladling that, you're going to have to be a little bit hotter because you're going to lose temperature in the ladle, lose temperature in your cold chamber, shot sleeve as you inject. So you're going to have to back figure to what my ladle temperature needs to be to get that injection temperature for that specific alloy. So we'll have to follow up on that later. The next question is, would one viewpoint be enough, meaning operator side versus extractor side, or both directions since there are shaded areas? Okay, so now we're back to talking about the infrared cameras. I think you could have to do, I always did it from the top of the tool, and I still had shaded areas where I had stand-ups. So I positioned the cameras, they were movable, and I positioned the cameras on my critical zones, and that's where I had my setup for that particular tooling. So if you could have multiple viewpoints, that's better. But like you said, there are going to be shaded areas if you have large stand-ups or stand-ups in the tool or deep pockets in the tool that you can't necessarily see deep into a pocket. So more cameras would be better. The last one says, can I show question 2 again? So let's go back. Very beginning. There's question 1. And here's question 2. Is there a commonly used hourly rate to operate die-cast machines of various tonnages when preparing a quotation? And I'm going to jump to what I summed up, and that is this, that there have been studies showing an hourly rate. Once again, this is back to 1994. There are not any current studies, and a lot of that is going to be with your location and economic condition of those locations, wherever the casting source is. questions back up. Okay, so the next question is die setup time shown. Did that refer to two dies that make the same part or two completely different dies? Is the trim tool considered in that as well? So in my SMED operations, I always consider the entire die-cast cell, not just the die-cast die. And I always considered moving from one die-cast die to a completely different die-cast die. So the parameters, the setup parameters, so the team consisted of not just the setup individuals, but the process individuals to put all the process parameters or pull up the correct program in the die-cast machine and make sure that we had the process parameters for the die that was going in. So it was considered to be a completely different tool, and the trim die was also considered in that because that's part of the process. The robot program, the sprayer program are also part of that same process. And if you have to change sprayer manifolds, and I didn't even get into that, there are a lot of quick change sprayer manifolds, or you have programmable sprayer manifolds or programmable sprayers if you're using a robotic sprayer. So that robot program in the sprayer would also have to be considered. But it's last good part to first good part, not just I've got the die set and I'm walking away from it. Now you can do the rest of the stuff. So are there any additional questions?
All right, guys, if you have more questions, if you want to just click that hand icon, that'll let us know that you're typing something in and that we should hang on the line until that comes through. Again, please feel free to email us or submit on that questions form if there is something else that you are looking to have answered. All right, I don't see any hands raised and I don't see any questions coming through. So I'm going to say that this concludes this week's episode of Just Ask Paul. If you have any follow-up questions, please feel free to submit those. If anything has come through that we missed somehow, we will address that offline. Thank you guys again for joining us today. Paul, thank you for putting this together. A lot of people have said that it was great. Thank you. And thanks, guys, and have a great rest of your week and a good weekend as well.